Alright, 4 lectures in. Actually, this is the 5th lecture, and we're finally getting into the nitty-gritty. I think that we have the background ideas of what is temperature. It's the average translational kinetic energy of a material. What is heat? It's the transfer of energy from higher temperature to lower temperature. And we talked about all the different ways that that can occur, and some reasons why the same amount of heat exchange doesn't always result in the same temperature change. And now we're going to get into thermodynamics. And thermodynamics is really the study of heat and motion. That's what this means quite literally. And if you have motion, then you're typically going to be able to have work. So it's a really important topic because prior to the point where we developed the steam engine, we were able to produce heat in great abundance, but all that we could do with the heat was warm things up. It's much more difficult to do work. And what was discovered was that there is a way to transform heat, basically, into something useful. And that's the whole study of thermodynamics. Now, a little bit of background in this, you can kind of look this over on your own, but just briefly, there's different ways that we can approach a system where we want heat to do work. The one case, the isolated, is a theoretical case, which means that nothing can be exchanged, no mass and no energy. And we can't actually achieve this, but we can come pretty close. So it's a useful tool sometimes for approximating what's going to happen in a system where the energy exchange is very low. The closed system is the more realistic sort of cousin of the isolated system, where we acknowledge that energy is going to be entering and leaving the system, but no mass can enter or leave the system. So it would be, for instance, like a container filled with some sort of a fluid. We can heat that up, we can take energy away from it, but we're not going to be actually removing or adding any fluid to it. And that's usually pretty easy to achieve. The last type of system is the open system. And in the open system, you can get energy in and out, but you can also move particles in and out. Now, we talked about the zeroth law, which basically says that if particles or if samples are at the same temperature, no heat's going to be exchanged. And if they're at different temperatures, the heat will go from the high temperature to the low temperature. The first law of thermodynamics was first formulated by James Joule, and it's really conservation of energy. So it's not a new equation per se, it's just a specific case of the equation. And so U is what we use to stand for the internal energy. And so this would be the change in the internal energy of the system. We're not usually that interested if the internal energy isn't changing to some extent, or if the possibility of change doesn't exist. And this will change based on 2 factors. If we add heat to the system, the internal energy of that system will go up. So this Q is the heat added to the system. If you take heat away from the system, Q would represent some sort of a negative number. This part is a part that I absolutely hate, this negative sign right here. It always confused me. I never quite understood it when I was in school. But what they're saying is that W represents the work done by the system. So our focus is always the system. What is happening to the system as far as heat being added to it. And then because we're interested in changing heat that we add to the system into work being done by the system, those are what the variables are. That's the whole purpose behind thermodynamics. Can we change heat into useful work? And so if the work is done to the system, it would be negative. That gives us a double negative, which would increase the internal energy. So if work is done to the system, the energy of that system goes up. If work is done by the system, the energy of that system goes down. I'm going to give you some examples of this, but I just want to briefly take you through sort of an alternate statement of this. So change in the internal energy is really just the final energy minus the initial energy equals Q minus W. And then we can rearrange everything. So if I move W over to this side, I kind of did a swapping of sides. I moved W over to this side minus initial energy over to the side, and then I just swap the sides. So I have initial energy, the initial energy plus whatever heat I add to the system equals the final energy plus whatever work was done by the system. And that's about it. It's really just conservation of energy. Okay, so let's look at some cases just very briefly here. Actually, before we look at any examples, let's just talk about how work is done in cases like this. Typically, the way that work is done is, let's say you have some sort of a gas, and you heat up that gas. Well, the gas heating up wants to expand. So if it's able to expand, then work is done. And we'll come back to this, but I just wanted to briefly explain how we're going to achieve work before we get into actual cases. Okay, what I have here is a container filled with some particles, and I'll make it look like it's a little bit more filled with particles here. So we've got this container filled with particles, and we'll say it's a gas. And these particles are then moving around. So we have particles moving in all sorts of different directions, some slowly, some more rapidly. And they're all kind of bouncing around and banging off of things. And what typically happens is some of them bang into this platform. So this is the container. And there's sort of a slidable platform here. And we put some weights on top of this slidable platform. And if the platform is staying in place, that means that the force that the platform is exerting downwards through the weight of these materials is equaling the force that's being exerted upwards by the particles banging into it. Obviously, this is not a constant thing, but because we have so many particles, I haven't represented it very well. We have so many particles colliding with this surface that it looks like it's a very constant thing. You might have slight ups and downs, but it would be too small for us to really notice what's happening. So you have the weight downward, you have the force of the gas, I'll put force of the gas upwards, and you have the weight downwards. And this is really, this force here is really the pressure times the area of this container. So if we look at what is the pressure of the gas, then multiply it over that area, that tells us how much force the gas is exerting as a whole. What this does for us, though, is let's say that we then take a fire. This is a fire, by the way. Very impressive fire. It gets even that bluish light in the middle there. Maybe a little less intense off towards the edges. But here's our fire. And the basic idea is that we're taking heat and we're adding it to our system. So what's going to happen is these particles are going to go faster. And if we have faster moving particles, I'm just going to take this and move it over to here. So we now have these faster moving particles. So this one's now moving, whoops. This one's now, I'm not quite sure why it's doing this to me. Okay, I think I've got it now. So this one's moving faster, and this one's moving faster, and this one's still a little bit sluggish, but it's moving faster, and this one's faster, and this one, and so on. What this is going to do is it means that we're going to have much more frequent collisions with the surface, and those collisions are going to be more violent. So what's going to happen is that we're going to, when we draw our forces that are acting, we're going to have this force of the gas, and the weight hasn't changed. So the force of gravity pulling downwards has not changed. So this means we now have a net force, which hopefully we still remember that also means that we have a net work being done. We're going to get motion. We're going to accelerate this. So let's say that this goes up a certain distance. Okay? So it's going to expand the volume. In order to determine how much work the gas is doing, not how much work is done total, that's kind of a different story. We're interested from our equation, delta U, equals Q minus W. We're interested in how much work is done by the gas, which is the force done, or the force exerted by the gas. So, in looking at this, the force from the gas times that distance is the work done by the gas. Well, the force of the gas, we already said, was equal to the pressure times the area, and we're multiplying that by the x. This area times distance is nothing but the volume change. And I didn't draw this three-dimensionally, and maybe I should have done so. But let's say that you have... This is a terrible container. This is your container. And it moves up to here. Okay, so it's moved through this distance x from down here to up there, and we have a certain area. And so what we've done is we've changed the volume by a certain amount. And so we wind up with the work is equal to the pressure times the change in the volume. If we haven't changed the volume at all, then we haven't done any work. Now, what this might wind up being then is that, let's just say this is 100 joules, so we added 100 joules of heat. Maybe this equates to 60 joules. And so what we would get then, if we're solving for the change in the internal energy of the system, is we would get 100 minus 60, because this is work being done by the gas. And so we have this increase of temperature, at least up to this point. We're going to have an increase in temperature because our internal energy has gone up. We've added energy to the system, even while it's doing some work, because we had it on a fire, basically. In the next lecture, we'll talk a little bit more about this type of a setup and look at some other things that we can do to try to get work to be done. And we'll talk about some specific processes, perhaps talk about some specific processes where this can happen.